Good evening, class. This is statics, week 5, Wednesday lecture. We'll finish up chapter 4 on force system resultants with a few other explanations of theory in the chapter, and then we're going to work several problems also related to chapter 4, and we'll finish that up today. First thing we're going to do is take a look at a 3D problem. We've done 2 3D problems. The first problem took a look at a force vector and the moment about a single point. The second problem we did, it had a force vector, and what we did is we looked at the moment about the y-axis. Today we want to take a look at a force vector F about some other axis in space, and in this case we're looking at the AC axis. So this problem asks what is the moment about the AC axis, which is this axis here, from this Cartesian vector F, which is 4i 12j minus 3k pounds. Okay, so we want both the scalar quantity and also the Cartesian vector. And once we get the scalar, the Cartesian vector ends up being very, very simple to calculate. Now, in order to do the problem, we need to find the unit vector, first of all, of AC. Okay, and the way we get the unit vector is, again, from the origin, 4i plus 3j. Okay, that describes this unit vector. So we have 4i plus 3j, and we divide by the square root of 4 squared plus 3 squared. And that gives us a unit vector of 8/10 I plus 6/10 j. So that's a unit vector of AC we have here. So the moment of a force about the AC axis, this is as a Cartesian vector, is equal to this unit vector dot RB, which is a position vector, across F, which is the force vector. And so what we need to do is find the position vector. Okay, which means we want to go from the origin, or anywhere from this line, actually, AC, and we know where it is from the origin. Okay, we can use it, find a position vector there. So that would be 4i plus 4i. Then it's going to be plus 3j, and then we need to get down to b, and this is going to be minus 2k feet. That's the position vector going from A to B, which is this right here. So it's 4i plus 3j minus 2k. There is another position vector. Again, remember, position vector is any point on this line to the vector itself. Well, point C is on AC. That's the end point. So if we can go from C, which is on AC, position vector then is just minus 2k. And so we have this as a position vector. I'll set both of these up, and it doesn't matter which one. This is easier to use calculation-wise, but this will get you the same answer as using this position vector. So the moment of a force about this axis is the unit vector dot RB cross F. And we can set this up in a 3x3. The first row is the ijk. In this case, it's the unit vector. If we were in space, we use just ijk. If it's in three-dimensional space, say you're taking it about the origin. Okay, in this case, the unit vector is the one we calculated. So this first row, this is the I, this is the J, this is the K. So it's 0.8, 0.6, 0. Okay, here it is right here. 0.8, 0.6, and there's no K, so it's 0. The position vector, we chose this position vector to be, and it was just minus 2K. So the position vector is 0, 0, minus 2, again, I, J, K. You could put this position vector in, and I'll show you that 3x3, 4i, 3j, minus 2k, and it would get you the same answer. And then the last row is the vector itself, Cartesian vector, 4i, 12j, minus 3k. We solve this, and I did it down here. Just briefly go through this with you. The first term is the 8 times this 2x2 here, which is 0, minus 3. 0 times minus 3, which I have here. And then when we go this way with the term, it's minus, and it's minus 2 times 12, which I have here. The second term is the j, which is, in this case, is going to be the 0.6. And this always, the second term, this always has a minus sign, so it's plus, minus, plus. So it's minus 6. And then we have this 2x2. So it's 0 times 3 minus 2 times 4 here. And then the last term is 0. We're multiplying by 0, so there's nothing in that last term. And if you do this calculation then, okay, with all these values, you end up with the moment of AC is equal to 14.4 pound-feet. Okay, to write this as a Cartesian vector, you simply take the scalar quantity of the 14.4 times the unit vector, which was 8i plus 6j, 8i plus 6j, and you end up with 11.5i plus 8.64j. Okay, and that ends up being the unit vector. So what makes this problem a little bit different is this first row, okay, which is the unit vector row. In just normal three-dimensional space, it's ijk. Second problem looked at specifically the y-axis, and this would have been 0, 1, 0. Okay, because we didn't have, it was the y-axis, we had no x or z-axis. And now we have this one basically in space, the UAC. And the other thing is position vector. That's a good question. Just what are the position vectors in a problem? And there are two position vectors. Again, you can take it from any point along the line in question. And this is AC. And the only way we can go here is where we have the coordinates for reference. So you can take it this way, or you can take it this way as a position vector. C is on the line and A is on the line. Oh, actually, this is what this second part would look like, using that second unit, 0.8, 0.6, and 0, and when you had the other position vector 4, 3, minus 2, do this calculation and you come up with the same magnitude, 14.4 pound-feet. Okay, so there's additional simplification for these problems, just as a brief review in what we're looking at. We have a general object or body. I have 4 forces acting on this body. They all have a common point of intersection at point O. And what we found with problems, we can add all of these vectors together, these forces, F1, F2, F3, F4, and come up with a resultant that would be acting at the center at some angle. So in terms of simplifying, we can simplify this 4-force system into a single resultant force. No moment, it's not going to create a moment. And so we go from 4 forces to 1 force. If we had a resultant force, in this case, we have 4 forces here, we can add these up and get a resultant force, but we also know if we're looking at this point in question, each of these forces are going to create some type of a rotational moment around this force, okay, because they're not acting through that point or through this point that we're looking at. So there's going to be a moment created by these forces along with the resultant force. And one of the things that you can do, and we'll show you this in a problem, is here's the resultant force. I'm going to position it some distance from that point O to create a moment that's going to be equal to the moment created by these 4 forces. And this would be the greatest simplification. I could show this resultant force at this point and show a moment around this point. But if I just put this single resultant force at some distance that would create that moment, this simplifies everything, and all we're showing is the resultant force at a distance. You can also do that with 3-dimensional space. Your book does it, and I'm attempted to do this like on this 2-dimensional paper, and didn't think I would make much sense doing that. So we'll just stick with that. A couple, 2 forces parallel to each other, same magnitude, F in this case, opposite directions, separated by a perpendicular distance D. This couple creates a moment. So what is this doing? It's rotating, okay, in the clockwise direction. And the magnitude of that moment is the force times the perpendicular distance. Or you could write it as vector quantities, m is equal to r cross f. I'll show you that also. Couples are equal if they produce the same magnitude and direction. Resultant of couples is the summation of the individual couples. And you remember the notation that we used as we some forces, we have plus forces and minus forces, plus and minus forces. We need to be able to add plus and minus. Same thing with couples. When we add couples, obviously a counterclockwise couple could counteract a counterclockwise couple and a clockwise couple, and there's a lot of interactions and counteractions that we're looking at. So we need to be able to add these, and we assign the plus and minus sign. Minus negative is clockwise, and positive is counterclockwise rotation. And so that allows us to add moments and couples. We treat them the same way. Okay, this is going to be the example of the problem that I want to take a look at. All we want to know is there are two couples acting on this structural element. There's 200-pound couple, distance of 1.5 feet. And there's a couple here, force F, and there's a magnitude on F. 12.5 pounds, I believe. Yeah, 12.5 pounds. I'll show you this in the example. So we see these are parallel because the angles are 30 degrees. The problem is we don't know that distance, perpendicular distance. So what I want to do is the following with that problem. Little diagram. Okay. Here's the 200-pound force. Okay, separated by a distance. Distance is 1.5 feet. Sort of hard to see on there. So this is 1.5 feet between the two. And here's what we're going to do with this 125-pound force couple at a 30-degree angle. I'm going to break this down into components. So I can find the y component. Okay, and I can find the x component. Here's the y component. Here's the y component here. Okay. The y components, there's a perpendicular distance, but the distance is the same, and these are opposite. One's counterclockwise, the other's clockwise. So those moments will cancel each other out. So we can neglect the y components contributing to moment. And so what we can do is use the x components. And this x component, we're looking at, this is an adjacent side to the 30-degree angle. So this is going to be 125 cosine of 30. And then this one would be the same thing, 125 cosine of 30 degrees. And we know that distance from here to here is 1.25. That's given on the problem. And so very simply then the moment resultant of this system then is going to be the 200 with this couple, resulting from the couple will be the 200 times the 1.5, and this rotation is counterclockwise. That's positive. This rotation is like this. So this is minus 125 cosine of 30 times 1.25. And what we end up with is 435.3 pound-feet, and we want to just use 3 places, so it's 435 pound-feet. Okay. So simplification of a force couple system. We'd like to take a system of forces and couples and have a simple force or a single force and a couple, basically a one, and these will describe external effects. And if the external effects are the same of a single force and couple as the original forces in couples, then that means the system has been simplified, and it's going to be acting in the same way whether you have the single force and couple as whether you have the multiple forces and the couple. Okay, so that it's the same body we're looking at. The result's going to be the same. So basically what we're saying is the resultant force is the sum of all the forces. The resultant moment about a particular point in there is equal to the sum of the moments, which we'll call the force moments, plus the sum of the couple moments. We treat couple moments and force moments as the same. They have the same sign convention. It's a moment. Doesn't matter how we calculate it. The reaction on a body and a structural element will be the same. So to break it down even further, and we were some forces in the X, we some forces in the Y, and we have a resultant force in the X, resultant force in the Y, and then we have a resultant moment, which is the sum of the force moments and the couple moments that we're looking at. Give us a resultant moment. What we want to do in structures, particularly once we get into the next chapter, rigid body equilibrium, we want to simplify the problems. This is a problem we're going to take a look at as an example problem. It's a vertical post. We've got 3 forces, a 300-pound force at an angle of 30 degrees, a 100-pound force. It's at a slope of 3, 4, 5, and we have a force perpendicular to the post, 200 pounds, and we give the dimensions 2 feet, 2 feet, and 2 feet at the bottom. And what we want to do, we want to simplify this to a single force in a moment, and we want to do this about point O down here. This is a support, probably a plate system, plate on each side, you can assume, and these would be bolts through here. And when we simplify this force system, that allows the engineer to design this support. And basically what that would mean, first of all, how many bolts do you need? And they've got 4 right here. So what type of bolt? And then more importantly, in terms of design, is what is the size of the bolt? What's the diameter of the bolt? And when you get into strength materials, the second course, you learn how to do that. And when I teach the strength sometimes the books don't really go into any big effort in terms of doing design at that point. You may do that in other courses, but I tend to introduce basic design. And this is one that could happen. It's a fairly simple design where you just find the cross-sectional area. But in order to do that, you need to know what force and moment is acting at this point. So that's why we're going to simplify this. So I'm going to redraw this here. Okay, I label the forces. So we want to replace this system with resultant force and couple moment there at point O down here. So what we do is we break all the forces down into X and Y components. So this 300-pound force is going to be, X component is 300 cosine 30. We'll sketch it out. It's in the positive X direction. The Y component is 100 sine 30, opposite, vertical. It's up, positive. This force, there's a negative X component. In using slopes, it's 4/5 of 150 pounds. So it's 4/5 of 150. The vertical component then is going to be 3/5 of 150, directed upwards, positive. And then we have this 200-pound force acting in the positive X direction. And that's positive Y, negative X, positive Y, positive X. And then all we do is sum forces in the X direction. So we add the X components, 300 cosine 30 plus 200 plus minus 4/5 150, which we get right here. And that resultant is 339.81 pounds, directed to the right. Okay, it's positive. Again, when we're doing calculations, you can carry the numbers out to whatever you want. In fact, it gets you more accuracy if you go ahead and carry decimals out. We do the rounding at the end. And then we do the same thing. We sum forces in the Y. So we have this 300 sine of 30 degrees. Okay, so 300 sine of 30 degrees. And then this is the 3/5 150. Okay, 3/5 150, and that's positive. And so we have sum of forces in the Y, positive 240 pounds. Okay, so we have an X and Y component. I just sketch it out here. Here's the 330, what was it? 339, and we had the 260. We know the resultant force then is the square root of the sum of the squares of the X and Y components, which is what we did here. Okay, X component and Y component. And carry out to 3 places, it's 416 pounds. And we also need to know the angle that it's going to be acting. Okay, so here's theta. It's the inverse tangent of the Y component. Okay, which is going to be the 240 divided by the X component, which is 339 or 340, 339.81, carried it out. And so theta ends up being 35.2 degrees. Okay, and so that's the answer. Resultant 416 pounds, acting at an angle of 35.2 degrees. So what we've done is take the forces, and we found the resultant force acting on here. That's a taste of design, knowing that force. And the second thing we need to do is calculate the moment about this point O. And the only forces that are going to contribute to moment are the X components. The Y components pass through this point, so there's no moment created. So this Y component and this Y component won't contribute any moment, just the X components, and there are 3 X components. Okay, this has a moment arm of 6. This one has a moment arm of 4, and this force has a moment arm of 2. So we do the moment calculations. And again, we want to keep track of the positive and negative. Negative, negative, positive. Okay, so we have the negative, negative, positive times the moment arms. And we end up with a resultant moment of 1,478.8 pound-feet. Okay. We want, again, it's negative. Okay, so we need to show the direction as part of that. What I want you to keep in mind now is the fact that we need to look at this at 3 places. And this is the first real, I think the first real test of the concept of the 3 places. 1,478.8 pound-feet. So we want 3 places, which takes us to 1.48. And the question is, what goes with the feet? And here I got kip feet. So here's what we're doing. Okay, we're moving 1, 2, 3. We're moving 3 places. Okay, that's 10 to the 3rd. So that's kip. So it's 1.48 kip feet. Okay. And the total moment is going to be negative. Okay, so that is clockwise. And what I would do is, part of your answer is indicate the direction. So indicate it either clockwise or counterclockwise. Okay, and a negative is clockwise, so I'm going to draw the arrow in the clockwise direction, and that would be my moment. Now with the moment, and particularly with the force, engineer can go back in and design that particular support. And look what we've done is we've simplified this system into a moment and a force. And I can do one other thing, and I haven't done it here, but what I could do is take this force using only this component, put it somewhere up in here, such that this 339 times some distance gives me this moment. So 339 times some y distance equal to this moment. I could position that force without the moment, and I would simplify this to just one force. Okay, position somewhere in here that creates this moment, resultant moment. Okay, at some distance. And again, the only component that creates the moment is this resultant X force. The Y doesn't. It passes through here. I didn't do that, but you could actually position that to have only one force acting on here, and it is the same as this force and moment acting down here. Okay. And I showed you this before, and this is sort of a rehash of what I did before. The only thing I did a little bit differently is you take a resultant force acting at some angle, and I took a resultant force acting some distance d from the point in question, which creates the same moment as you would have here with these forces. It's just a different way to show a simplification problem. We're going to end this talking about forces on a beam, which is going to lead us into the next chapter, rigid body equilibrium. And this is going to be an interesting chapter. It's probably one of the most fundamental chapters that we're going to deal with, is the chapter 5 that we're going to talk about, rigid body equilibrium. So let's look at the types of forces that we're going to see on a beam. Here's a beam, 10 feet long. I draw a support that looks like this. This is a pin, and we'll learn what a pin is. And this is a roller on a simple beam. And we'll talk about what a roller does. That's in the next chapter, but that's a pin and a roller. What I want to concentrate on is the force. We just showed concentrated forces, okay, before. Okay, so this would be the type of beam that we've shown. We'll put a force in here, or maybe we can show a couple, and some even at an angle. It's a single concentrated force. We also going to have problems with are called uniform distributed forces. So the way we show this with this type of notation, okay, we'll draw little arrows down here indicated there's forces along this distribution. In this case, it's across the entire beam, 10 feet. And the way we label it is the pounds per foot or the newtons per meter. So this is 100 pounds per foot of length. When we solve the problems, we can't work with this. Okay, what we want to do is draw the free body diagram. We want to reduce this force into this single concentrated force. So 100 pounds over 10 feet is 1,000 pounds. Okay, so we have 1,000 pounds, and we need to dictate where it's going to be acting. It's going to be acting at the centroid of this area, and this is a rectangle. So the centroid, is at the center, and so this is going to be 5 feet over, and we always measure from the left to right, always. There's some exceptions, but usually it's from the left to the right. So we dimension this 5 feet, 1,000 pounds. So instead of this beam, we work with this beam. Very simple to solve. Reactions here are 500 and 500. What we want to solve for are the resultant reactions. Okay, that's basically what rigid body equilibrium is about. Okay. So the second type of load is called a uniform varying load. And in this case, I don't have to start it here at the end point, but for convenience, we did. It's a triangular load, 0, and then what we give is the load at the maximum point on here. And this is 100 pounds per foot. Okay, in other words, it's going from 0 to 100 pounds, uniform varying. And the way we label it is 100 pounds per foot at this particular point. So again, we don't want to deal with this. What we want is a single beam with this as a single point. And so what we have here, this was a rectangle, base times height. Okay, 100 pounds per foot, base is 100, or is 10 times 100. Well, this is just a triangle. So the resultant force is 1/2 the base times the height. Okay, the base is 8, the height is 100. So the resultant force is 1/2 of 8 times 100, or 400 pounds. Okay, that's the area of this triangle, 400 pounds. Question is, where does this act on the beam? Well, this is a triangle, and the centroid of a triangle, and you should know this, starting from this point, it's 2/3 the distance, or 1/3 the distance from the point to the right. And again, typically we measure from the far left to the right. So it's 2/3 this distance, okay, which is 1/3, 2/3 of the 8, yeah. So 16/3. So that's 5.33 feet. So instead of drawing this beam, I draw this beam, a concentrated load of 400 pounds, acting 5.33 feet from the left support. This I can solve very simply. This I can't. Okay, so this is a simplification. A third type of load system that we will commonly see looks like this. I put a line here to show what we're going to do. It's up here, vertical, and then there's a triangular part here. So what we have, in effect, is a trapezoid. And you can work this as a trapezoid, area of a trapezoid. But you need to know where the centroid of the trapezoid is. I can't tell you offhand. I don't work with trapezoids very often. So I can't tell you offhand where the centroid of a trapezoid is. But what I can do is break this in, this is the way I would do it, break this down into a rectangle shape and a triangle shape. And we just did a rectangle and triangle, and you know where the centroids are. So the triangle, or the rectangle, is 400 over 8 feet. Okay. And the triangle then is 8 across here. And this side of the triangle is 100 minus 40, or 60. So 1/2 base times height is 1/2 of 8 times 60. The rectangle portion is 8 feet times 40. So 8 feet times 40. Okay. And what we do is we would have two forces, the rectangular force and the triangular force. And the triangular force is 320, and the rectangular force would be base times height, 40, 320 and a half. Okay, so we will have two forces, one centered here, and then one centered over here. 2/3 the distance over from 8. Okay, so at 4 feet and at 5.33 feet, we'd have the two forces, one from the rectangle and one from the triangle. And there is one other type of force system, and that is if we have the force as some function of x over some distance x. I will not give you any problems like that. Here's one that worked out as an example. This is the force system on this 6-meter beam, and this is what the force looks like as a function of x. Actually, it's x squared minus 4x plus 60 kilonewtons per meter. And what you do is you integrate this area from 0 to 6 to determine the total force, and then you can locate the centroid of this using this equation down here. Okay, the integral of the centroid x sub c, differentiating the force resultant and divided by the integral of the force resultant. And if you're interested, you can follow this integration. I won't give you that problem. The only problems that we'll look at will be a concentrated force, a uniform distributed force, a uniform varying force, or a trapezoidal force, which I've broken down into a triangle and also a rectangle. And that closes our discussion in chapter 4, force system resultants. Next week, we start in chapter 5, rigid body equilibrium, and we also have our first exam. And I will go through a brief introduction to chapter 5 and a review for the first exam. And then the exam will be on Wednesday. And if you look in your syllabus, it's detailed on if you just simply can't make the class time, you let me know before the exam, and we'll make arrangements through the testing center on what you can do to take the exam. Okay, so make sure you understand what the syllabus says. I discussed that in a couple of different points, and that was on the first lecture, first day, and it's in the syllabus. So be aware and don't let that exam slip by you without doing what you need to do in order to take it. Again, the preference is you attend the class and take the exam during class, but for some reason, if you can't make that, let me know and we'll make arrangements for you to take the exam. Have a great weekend, and I'll talk to you next week.